Hello, this is Fazal Wahab. You are watching my YouTube channel. We will continue the same topic today, and that topic is vector quantities. And we are solving the problems of vector quantities, the chapter vector problem, vector quantities. So the next question, the next problem that we are going to solve today is 2.12 and 2.13, but 2.12 is similar to 2.13 and 2.13 covers 2.12. Therefore we don't need to solve 2.12. We will solve the problem number 2.13. The problem is on your screen. The question is, the line of action of force F is equal to I minus 2j passes through the point whose position vector is minus j plus k. Find A, the moment of F about the origin. Number B, the moment of F about the point of which the position vector is I plus k. So the force has been given here. It is I is equal to minus 2j. One of the position vector is minus j plus k, and for A, the second position vector is the origin, while for B, the second position vector is I plus k, and we have to find out the turning effect or the moment of the force about the origin and about the position vector I plus k. So let's solve this problem. Okay, the force is F is equal to I minus 2j. This is the force, and one of the position vector, which is R, is equal to that position vector is minus j plus k, minus j plus k. This is the position vector, and the turning effect, or the moment about the origin. Moment about the origin. We have to find this one. So the moment about the origin, if we take it R1, then the position vectors for the origin, that will be equal to 0I plus 0j plus 0k. This will be the position vector for the origin. Okay, this is the cardinal axis, and this is plus y and plus x. Okay, and this point is the origin. This point is called origin. This point is called origin, where the y-axis is also equal to 0 and the x-axis is also equal to 0. So we can write the vector for this point is 0I plus 0j plus 0k, meaning that x-axis is also 0, y-axis is also 0, and z-axis is also 0. And for example, we have the position vector, which is minus j plus k, mean that the y axis is in negative and the z axis is in positive. So we can write it somewhere here, but doesn't need this one. Okay, let's say this is the position vector at this point, and it is minus j plus k. Okay, now we have to find out the moment about the origin. So the origin will become the pivot for this one, and the force is applied on this point. This is the force for which the vector has been given here. It is I minus 2j. The force is applied on this point, and there will be a turning effect because of this force, and this body will move about the origin, will turn about the origin in this direction. So we have to find out the turning effect of this force about the origin. This will become the moment arm. You see this one, this will become the moment arm for which the vector is minus j plus k, and this this is the force which is equal to I minus 2j. So we have, for A, we have to find out the turning effect or the moment is equal to R cross F. Okay. Now, how this is the vector product? We need to find out the turning effect, the torque, which is a vector, by multiplying a vector which is a position vector or moment arm with the force which is also a vector. So this is a vector product, and to find out the product of the vector product, we need to use the matrix method. This is different from the scalar product. Scalar product, we are just multiplying this vector with this vector by a simple algebraic method, but to find out the vector product, we need to find out the matrix method. Now, how can we do this one? What is the matrix method? Okay, so torque will be equal to R cross F. For R cross F, we are using the matrix method. I, here is I, J, and K. The first row will be for the unit vector. We will put the unit vectors in the first row, I, J, and K. And then for R comes first, the second row will be for the R. And for the R, here it is 0I. We don't have any horizontal component of this position vector, so we'll put 0 for the horizontal component. Here is 0. And for J, it is minus 1 here. That is, the magnitude of this vector is minus 1. And the magnitude of this vector is 1. So the coefficient with the unit vector is showing the magnitude of the vector. So here it is minus 1. Minus the magnitude of this vector is minus 1, and the magnitude of the vector, the component of the vector along the y-axis, that is also 1. And for force, the magnitude of the horizontal component is 1I, so it is 1 here. And for the vertical component along the y-axis, the magnitude of the that component is minus 2, and here it is 0 because we don't have any component of this force along the y-axis, z-axis. So we'll put 0 for this one. And now we will use the determinant method to find out R cross F. So for torque, determinant method, how can we do this one? I is here, I, and this column and this row of which the I, the horizontal component, is a part. We will delete this one and this one. This row and this column will be deleted. We will get this matrix. You see this one? This matrix. And minus 1 and 1, minus 2 and 0. Okay. Here is minus. Now remove this one. Okay. Here is minus. Minus is in the formula for the determinant. There will be minus. And J. Now delete this one, this column and this row of which the J is a part. J is the part of this column. We will delete this one. And J is part of this row. We will also delete this row. So when we delete this one, and this one, we will get this one, 0, 1 and 1, 0. The matrix will become 0, 1 and 1, 0, and then plus K. Plus is in the formula for the determinant. So plus and K, and delete this column and this row. You will get the 0, minus 1 and 1, minus 2. 0, minus 1 and 1, minus 2. Now just solve this one. Minus 1 multiplied by 0, minus 1 multiplied by 0, and then there will be a minus in the formula. Minus means the product of this diagonal minus the product of this diagonal. Okay, so the product of this diagonal is here, minus the product of this diagonal is minus 2 multiplied by 1. Okay. Now it is minus here, we will put minus here, and then j, unit vector is j, and the product of this diagonal minus the product of this diagonal. 0 multiplied by 0 minus 1 multiplied by 1. Okay. Then plus k, and again the product of this diagonal, who is minus 2, 0 multiplied by minus 2, minus 1 multiplied by minus 1. 1 multiplied by minus 1. Okay. Now we will solve this one. Here is 0 minus minus plus 2, 1 is a 2. So 0 plus 2i. Okay, minus 0 minus 1. 0, 0 is a 0. 0 minus 1, 1 is a 1, and it is j here. Okay. And minus 2 multiplied by 0 is 0, plus 0, and minus minus plus 1, 1 is a 1, and k. Okay. Now 2i, 0 plus 2 is 2. 2i minus minus plus 1j, we don't need to put 1 here. Plus 1j, don't need for 1 here. And plus 1k, don't need for 1 here as k. So this is the torque, the turning effect of the force, and that is equal to 2i plus j plus k. Okay, now part B. The position vectors for which the turning effect will be produced about that position vector is R2, and R2 has been given here. It is equal to I plus k. This is the position vector R2, and the turning effect will be produced about this point. Therefore, we will the resultant moment arm or the position vector will become R1 minus R2. So R1 is equal to minus j plus k and minus I plus k. Okay, minus j plus k minus I and minus k. So plus k and minus k will be cancelled out with each other. We will get minus I minus j will be the resultant vector, resultant position vector. You will get the moment arm which will be equal to R. Okay. Now T is equal to R cross F. For R, we will use the matrix method. I, J, and K. Okay, for R, it is minus 1 and minus 1, minus 1, minus 1, and 0. For F, it is 1, minus 2, 1, minus 2, and 0. Okay, now we will use the determinant method to solve for the turning effect. Okay, so torque will be equal to, we will put I here, and then a matrix will be formed. By deleting this column and this row, so we will get only minus 1 and 0, minus 1, 0, minus 2 and 0. Okay, minus, there is a minus in the formula, minus j, and again there will be another matrix. Delete this column and this row is minus 1, 0 and 1, 0, minus 1, 0 and 1, 0. There will be the matrix, and plus k, plus is in the formula here, plus k. Delete this column and this row is minus 1, minus 1. We will get minus 1, minus 1, and 1, minus 2. Okay, now use these matrices and solve this one. Okay, how can we solve this one? Now, how to solve this matrix? The product of this diagonal minus the product of this diagonal. So, minus 1 multiplied by 0 minus 2 multiplied by 0. Okay, then minus j, product of this diagonal minus the product of this diagonal. Minus 1 multiplied by 0 minus 1 multiplied by 0. And then plus k minus 1 multiplied by minus 2 minus 1 multiplied by minus 2, and minus is in the formula 1 multiplied by minus 1. Okay. Now I is here 0, minus 1 multiplied by 0 is 0, and minus plus 2 multiplied by 0 is 0, minus plus 0. Similarly, minus j will be in its own place, and again here is minus 1 multiplied by 0 is 0, or minus 1 multiplied by 0 is 0. It is 0 minus 0 j, and then plus k, and minus plus 2 1 is a 2, plus 2, and minus plus 1 1 is a 1. Okay. Now we are getting 0i here, 0i minus 0j, and plus 2 plus 1, 3k. So finally we will get the torque which will be equal to 3k, because we don't need to write 0i and 0j. So just only 3k is the final answer. And this was the problem number 2.13, and part A we have already solved this one. This is the part B, and the final answer of question number 2.13. We have completely solved the question.